Hi everyone, today I want to present you our presentation about neutron porosity log. This presentation prepared by second year students of Kazakh British Technical University, Okay Eduard, Turigaliyev Aldiyar, and Galimjanov Alisher. Our supervisor, Master of Science in Petroleum Geology, Nadir Ablay. It's our content for today's presentation. It concludes introduction, history, basic physics of neutron log, environmental correction, principle of operation, interpretation, applications, control questions for audience, and conclusion. And let's start our presentation. Let's move on to the first part, and let me to start. About introduction. This presentation focuses on the basic interactions between the tool signal and measured information that help characterize the formation. It's not intended to be a comprehensive review. In each log, a signal is emitted, interacts as it passes through the formation, and is detected either up or down hole of the source, as follows. First is acoustic log. Source are sonic waves. Formation refracts the waves, and the receiver detects transmitted acoustic waves, like compression, shear, and Stonian waveforms, and identifies travel time. Density log. Source emits gamma rays, which are considered energy photons, interacting with electrons, like Compton scattering, causing loss of energy. From the loss of energy, the density of the formation can be obtained. And about neutron log. Neutron log is a reaction between radioactive elements, emits fast neutrons, which collide with the nuclei of other atoms, most importantly hydrogen nuclei. The detectors count the slowed neutrons deflected back to the tool. An apparent neutron porosity can be obtained based on the hydrogen index. And excellent references are listed at the end of this presentation. Its interpretation data based on the some tools on one well. Now I talk about history of neutron log. The neutron porosity log first appeared in 1940. It consisted of an isotopic source, most often plutonium, beryllium, and a single detector. Many variations were produced exploiting both thermal and epithermal neutrons. The now standard compensated neutron porosity logging, shorted CNL. In common use since the 1970s, is still a very simple tool. Basic physics of neutron log. The neutron log contains a radioactive source, which by means of reaction between elements emits fast, high-energy neutrons. As the neutrons enter the formation, they collide with the nuclei of other atoms and slow down, loss of energy. Note, the terms high-energy neutrons and high-velocity neutrons are the same, since the mass of the neutrons is constant. There is a connection between high porosity and low gamma ray counts. If we have high porosity in the formation, we have low gamma ray counts, and vice versa. When we have high hydrogen content, we have neutrons are slowed rapidly, and neutrons are captured close to source, and little radiation reaches the detector. When we have low hydrogen content, neutrons are slowed down less rapidly. Many neutrons captured close to source, and significant radiation reaches the detector. Let's move to the second part. Now about environmental corrections. The neutron log needs corrections for borehole size, formation temperature, formation pressure, mud salinity, and buried content in mud. The borehole size is automatically adjusted based on the caliper log readings. Principle of operation. A historical perspective of the range of neutron logging tools can help to prepare you to work with different vintages of logging data. Early neutron tools, known as GNT type tools, consisted of a chemical source and a single detector which measured neutron capture gamma rays. This tool, a qualitative indicator of porosity, was badly affected by hole size and the salinity of the borehole fluid or formation water. To properly understand the operation of the CNL logging tool, we must first understand the distribution of the thermal neutrons as they move away from the source. Each collision reduces the energy level of the impacting neutron until it reaches an intermediate energy level. At this interstate, a neutron is called an epithermal neutron. As epithermal neutrons collide with more nuclei, they lose additional energy until they come into general equilibrium with the surrounding nuclei. At this level, they are called thermal neutrons. Mass neutron tools detect returning thermal neutrons. The compensated neutron lock, briefly CNL, was introduced in the late 1996 with two detectors of thermal neutrons. The thermal neutron flux is defined as the number of thermal neutrons crossing unit area and unit time. The neutrons that don't reach thermal velocities and are not subject to nucleus capture are called epithermal neutrons. The compensation neutron lock uses two detectors, a near and far detector, as you see in the picture. An estimate of the size of the neutron cloud around the source is calculated based on the ratio of the count rates at these detectors. The two detector lock counts both epithermal and thermal neutrons. It does this so that a meaningful population of neutrons can always be counted. This makes the lock reliable in a sense, but creates an accuracy problem, because the thermal neutrons population has been reduced by capture absorption, making the hydrogen index less accurate. Now let's tell about interpretation. If the lithology is known, the neutron lock can be used to calculate porosity. Generally, the neutron and the density locks are run together. The photoelectric lock may also be run to further improve the lithology description. For example, a rock matrix with a 50% limestone and a 50% sandstone with 20% porosity will be halfway between the limestone and sandstone lines, as shown on the cross plot on the left. The cross plot is correct for readings in the invaded zone using freshwater muds. The MAN lithology plot is used to identify a complex mixture of sandstone, dolomite, and limestone using all three porosity locks. The rationale for the AMN plot is that the porosity should be the same in all three porosity locks for the same composition of lithology. Modern lock analysis today allows the inclusion of numerous minerals, including shale and various clays, into a lithology model. The computer program then must calculate the percentage of each component based on all relevant locks, including acoustic, spectral gamma ray, and NMR, if available. The PE lock is particularly useful in complex lithology determinations, as the readings are much more sensitive to lithology than porosity. And the last part, our presentation. Applications of neutron lock. These very important type of geophysical exploration methods. Firstly, applicate for porosity, which displayed directly on the log. For lithology identification, with sonic and density. For gas indication, with density. For clay content and shaleness indication, with density. And for correlation, especially in cased holes. And to sum up our presentation, we prepared for you some questions. And if you have been attentively enough, you can easily answer to our questions. And first is, in which year in first time neutron logs is appeared? They first appeared in 1940. Decrypt the CNL. It means the compensated neutron log, briefly CNL. And the last question. What is the connection between the porosity and gamma ray? As you see, if you have high porosity, the value of gamma ray counts is low, and if you have low porosity, the values of gamma ray counts is high. The neutron log is sensitive mainly to the amount of hydrogen atoms in a formation. Its main use in the determination of the porosity of a formation. Neutron logging is used to solve a variety of problems related to the prospecting and exploration of oil and gas and control over the exploration of these deposits. Neutron logging methods have a shallow depth of research, and the results are much the distorting influences the diameter of the hole, filling its liquid properties, the nature of the filter cake. And our references for today's presentation. Thank you for your attention.